Are we good to go? Yeah, thank you. And good afternoon, everyone. My name is Xiang Yuan, and I'm a PhD student from the University of Alberta. And my professor, Professor Xinming Li and Professor Qipei Mei. And thank you for all you all to join us and listen to my research, which is about the lightweight on-device computer vision augmented reality, supports task performance and perceptual situation awareness in construction. And basically, our focus is mainly focused on how to apply the human factor principles into the construction workers and try to improve their task performance and try to make them to assist their daily work. And here is the research agenda about today's topic. I will start it from research motivation and gaps, and then go through the system framework and methodology, experimental design and evaluation, and finally, we will come up with a discussion and the future directions. So here we are mainly focused on how to evaluate the cognitive burden from the construction workers. As we all know, construction workers mainly need to identify the correct components, locations, and their status in the dynamic and clusters construction site. And they also need to interpret task sequence and spatial relationship, while meanwhile, they need to verify the current actions while anticipating next steps. And things makes a little bit worse when the digital principles come to the construction site and they need to manage the increasing information density. So here is the core challenges. Construction work put higher requirements on situated judgments and make the task execution information intensive and cognitively demanding. What the original guidance tools they cannot provide is the paper drawing and the manual require the mental translation, and the video tutorials are not responsiveness to the current site conditions, and their verbal instructions are difficult to standardize and revisit. So the thing is, it's very simple to provide information, but the real challenge is how that information is connected to action in context. So we think augmented reality could be one of the solutions to this problem. They can provide the instructions directly in the worker's field of view. However, most construction AR systems remain display or centered, which means the instructions are predefined. They cannot be responsive to the current situation of their workers. And they still need to perform the visual search manually. And the similar components and the visual distractors can create confusions. So we identified the research gaps. AR needs real-time environment perception to support level 1, which is the task-oriented situation awareness. So we try to answer the following 4 research questions. Does computer vision aided AR enhance task performance in dynamic construction sites? And how does computer vision aided AR affect workers' task-oriented situation awareness? And how do users perceive CVAR in terms of guidance, effectiveness, response prompt stability and the information trust, and thus this task complexity could moderate the effects of CVAR on performance task. Here is how we did our system. The first above one is the blue dash, and you can see here is the static AR, which can only provide the fixed instruction panel. Workers can only manually locate the components. And below in the orange line is the computer vision aided AR, which we already, based on the static AR, we add more function like the real-time object detection and the spatial overlay. And here is the overall pipeline of how we developed our CVAR systems. As you can see here, at the very beginning, we captured the RGB frames using the HoloLens, which is developed by the Microsoft company. And then we trained the YOLO V8 model, which is completed in the computer. And after that, we deployed the on-device object detection function into the HoloLens. And then we try to use the 2D to 3D spatial mapping and finally overlay the generation and updates it in the HoloLens. And here is our basic results about this model. As you can see here, we used the YOLO V8 model, and we collect almost more than 17,000 images, and we just identified the 16 scaffold components. And the overall performance is pretty well for the devices like the HoloLens. We reached the 923 FPS. And here is how we conducted our experiment. We recruited 10 users, try to use the counterbalance experiment. They will go through each condition of the both static AR and CVAR, and they will go through 3 different levels of easy, medium, and hard mode of the experiment, which is they have 1 target of 1 distractor, 2 distractors, or 2 targets of 2 distractors. And here is our evaluation framework. First, we evaluate from the task performance, situation awareness, and the system quality. And as you can see here, task performance is evaluated by completion time, error count, and first attempt corrector. And the system quality subjective evaluation is self-developed and self-evaluated and self-verified the questionnaire. And as you can see here, the situation awareness is evaluated by the well-adopted questionnaire. And it could have 3 different aspects: the understanding, demanding, and the supplies. It's basically 3 different aspects of the situation awareness, which is understanding is how the information you are going to perceive. And the demanding is what kind of mental demand you may have while you performing this task. And the supply is how the system can support you while you performing this task. And we have those 3 different findings. The first one is computer vision aided AR can improve accuracy more than speed, which means the overall completion time showed a faster trend, but it was not significant. But the error count and the first attempt, they have the very significant results. So we may come a conclusion that CVAR improved the perceptual reliability during the component identification. And the second finding is CVAR was the most effective under the hard task. As you can see, the evidence is here. While you under the hard task conditions, CVAR produced significant benefits, which you can see here: the completion time, error count, and first attempt correctness. They all have the significant increased results. And this kind of pattern cannot be found when we compare the easy and medium task. So we can come an interpretation like the CVAR is most valuable when visual ambiguity and the component similarity are high. And the third finding is perceptual benefits come with a cognitive trade-off, which means they have the higher perceptual understanding, the greater perceptual attention supply, while they also increased their perceptual demands. That is what we will not expected at the very beginning, because that means the users, the perceptual cues expands what workers can see, but the density, stability, and the timing must be managed to avoid their attentional overload. And here we can come to the conclusion. The CVAR enhanced the task-oriented situation awareness by improving their perceptual grounding. And the CVAR significantly reduced the component identification errors, the overall time, and their benefits was strongest under the high complexity and visual ambiguous task. So this come up with some implications when we try to design some similar systems in the construction site. We need to deploy the CVAR selectively while the visual ambiguity is high. And we need to improve and prioritize the cue stability, timing, and density. And the limitations is very, very clear. Like we just conducted the control indoor environment, and we need to have some experiment on site. And in the future, we will come up with some more like the multimodal evidence to qualify the situation awareness. And here is all the reference we used in this presentation. And thank you for your time, and I'm very welcome for any questions or feedback.
Thank you.